So, two old fish are on their morning swim around a coral reef one day, and they come across some younger fish. And as they pass, one of the older fish turns towards them and says, "Hey boys, how's the water?" And then they swim off, just a friendly gesture. Well, this leaves the younger fish looking befuddled. They turn towards each other and say, "What was that old codger talking about?" "Yeah, what the hell is water?" So that's an old joke that I heard told by David Foster Wallace, which kind of gets to the heart of this lecture. So this is an aqueous geochemistry course. It's a class about chemical reactions that occur in water. But often water falls into the background of these reactions. It's kind of an unseen player in these reactions. But actually the properties of water are vitally important to driving what chemistry is possible to occur in water. So today in this lecture, I kind of want to bring some of these properties of water to the foreground, bring them to your attention, and discuss what is unique about water that allows a unique chemistry, aqueous chemistry, to occur in it. But just to step back a sec, this is the first lecture in this module, so I want to just go through the overall module learning objectives, and then we'll launch into some properties of water. So, in this module, by the end of this module, you'll be able to first outline the properties of water that are important for geochemistry. Secondly, you'll be able to calculate concentrations of solutions in a variety of units. And thirdly, you'll be able to describe the typical solutes that are found in environmental waters. So this module is a general overview of the properties of water and environmental waters. So by the end of this video, you should be able to name and describe 5 physical and chemical properties of water that are critical to the understanding of geochemistry. So we'll just launch right into that. Water, H2O, dihydrogen monoxide, clear gold, I like to call it. Okay, got a little corny. But anyway, moving on. This is a water molecule. You've seen a water molecule before. You have 2 hydrogens bonded to a central oxygen with a 120-degree bond angle between the 2 hydrogens. And these bonds here are covalent bonds. So you'll recall that a covalent bond is a bond where 2 atoms share 1 or more electrons. But this isn't an equal sharing arrangement going on here. You'll recall that hydrogen is a very weakly electronegative element. Oxygen is a very strongly electronegative element. And electronegative elements are elements that really want to attract electrons to each other. And so oxygen, being a much more strongly electronegative element, is drawing the electrons in this bond towards it. So this means that in this bond, there's an electron floating between these two atoms here, but it's spending much more time hovering around this oxygen than it is spending time hovering around the proton that makes up the hydrogen nucleus. And so, what does this mean? This means that this atom creates a dipole moment. The electron spends more time over here, so this side of the atom becomes more electronegative, negatively charged. This side becomes more positive because the proton's just hanging out here without an electron hanging around a bit. So you have 2 of these hydrogens doing this, and so this creates, along this axis here, the vertical axis, the dipole moment, where this half of the atom is negatively charged, this half of the atom is positively charged. So this brings me to the first property that I wanted to discuss with you, and that is that water is a polar molecule. That's what we mean when we say that it has this dipole moment here. It has a positive end and a negative end. So why is this important for geochemistry? Well, let's consider this sodium chloride here. This is a salt, just normal table salt. It's composed of a sodium atom and a chlorine atom. Sodium is very weakly electronegative. Chlorine is very strongly electronegative. So when you have a bond between these two, they are sharing this electron very unequally. In fact, the electron is spending almost all of its time around this chlorine, such that if this molecule dissolves, the electron will leave with the chlorine, making it a negatively charged chloride ion, and the sodium will just hang out with a positive charge on it because it's totally lost its electron. So this is an ionically bonded atom, and when it dissolves into solution, what happens is this positively charged sodium atom, or sodium ion here, it gets swarmed by all these negatively charged oxygens. So you'll recall that opposites attract. These negatively charged oxygen parts of the dipole in the water molecule all surround this sodium atom. And conversely, around the chlorine, you have all the hydrogens butting up, trying to get a little bit of the negative action that's happening on this chloride ion in solution. And so what this does is it prevents the sodium and the chloride from coming back together and reforming a ionic bond with each other. And so this is how things that are polar remain in solution. You have the atoms, or the ions, I should say, getting surrounded by water molecules, and that's what dissolves things. You have water separating things that could otherwise combine and form a solid or a liquid that's not mixable in water. So water acts as a solvent of other polar molecules. Now it's important, here we have an example of an ionically bonded salt, sodium chloride, but other polar molecules are not necessarily ionically bonded like this, and they don't necessarily separate into ions. So for instance, an example that a lot of college students are familiar with is ethyl alcohol, which has a dipole moment here on this oxygen hanging over here. This oxygen is electronegative because it has a hydrogen hanging out down here. So this is a polar domain of this molecule. And what this does is it allows ethanol, or ethyl alcohol, to be dissolved in water. So this is an example of a covalently bonded molecule that nonetheless has a dipole moment, just like this water molecule does, and that's what allows alcohol to be dissolved in water. So the next property I'd like to touch on is the bizarre temperature density behavior of water, which you are probably already familiar with. So this graph shows this. On the x-axis you have temperature from frozen water at negative 150 degrees to vaporized water at 100 degrees. And on the y-axis here you have the density of water. So higher density water, lower density water. And of course the first thing that you notice is that when you have this phase transition at 0 degrees right here, there's a sudden decrease in density. Ice, solid water, is less dense than liquid water is. And so this results in the property of ice floating. And this is in contrast to almost every other substance in the universe. Second thing that I want to note happens up here, which is zoomed in over here. This little inset graph right here is just a zoom in of this area right here. And that's that water has a density maximum, you can see right here, at 4 degrees. So colder water, water that's at 0 degrees, is less dense than water that's at 4 degrees. And after 4 degrees, you have the typical temperature-density relationship that you expect from most any other substance again, where density decreases with temperature. So most every other substance, you have a strictly monotonically decreasing relationship of density and temperature, but water has this hump-shaped relationship with a density maximum at 4 degrees. And this is actually vitally important for processes like ocean mixing and stuff, particularly at the poles, which we won't really touch on too much in this class, but this is a very important property. The most important result of this, though, is that ice floats. And this is super important for aquatic ecosystems and aquatic geochemistry, because if ice didn't float, if water is more dense in its solid phase than it is in its liquid phase, then what would happen is, as the temperature decreases and the top of a lake freezes, that ice would sink to the bottom and remain frozen at the bottom. And so what you would have is you would have lakes freezing from the bottom up. You would have oceans freezing from the bottom up. And this would result in permanently frozen lakes and completely solidly frozen lakes in places. Whereas, and obviously kill all the biota in that lake, for example. Whereas what we have here is we have ice forming an insulative layer at the top of the lake such that the water below can remain unfrozen and you can go ice fishing in the winter. This is a very important property for geochemical processes that occur in freshwater bodies particularly, but also in polar oceans and such. So the last property of water that I wanted to discuss is its adhesive and cohesive properties. So what's adhesion? Adhesion, like an adhesive, it means sticking something to something. And water sticks to things. Those polar domains that we talked about in a water molecule allow it to be attracted to other polar domains and allow it to give it some stick-to-itiveness against the force of gravity. And then cohesion, together, means that water likes to stick to itself. Water molecules are attracted to it themselves, and this gives rise to the property of surface tension. A bead of water that you put on a desk, if there's no surface tension, you'd expect that to just flatten out against the force of gravity. But water sticks together and makes it a bead. So that's a force, a cohesive force that's drawing the water together. And this is vitally important for places like soils, like indicated here. So these giant gray boulders are actually just tiny soil particles really, really zoomed in. And on each of these soil particles, you have tiny films of water developing. And those films of water stay in place in the soil against the force of gravity by these adhesive and cohesive properties. So the water is sticking to the soil particles themselves, and then the water is also sticking to itself and working itself into smaller and smaller crevices by these cohesive properties that develop an amazing degree of surface tension on the water, such that in really dry conditions, these water films are bound so tightly to the soil particles that you can't even release this water by baking it out in an oven at like 400 degrees Celsius. So there's an amazing amount of suction force that can be generated by water films due to their adhesive and cohesive properties. This is also what allows water to be transported in a tree, up the xylem of a tree, is that the water is adhering to the sides of the walls of the xylem tissue in a tree. These are the straws that draw water up into a tree. And water is evaporating at the top of the tree through the leaves, and this evaporation makes a progressively more and more suctiony force that draws water up the xylem of a tree via capillary flow. And this is all driven by the adhesion and cohesion of water. And so this is important also because as soils become progressively drier, like I said, so this is a very wet soil, water is indicated in black, this property allows water to be held more tightly and tightly and tightly to soil particles. And there's a lot of really interesting chemistry that happens at the boundary of soil particles and these thin water films. This is where a ton of geochemistry happens, and this is why soils just don't drain out against the force of gravity. This is why soils can hold water, enabling plants and enabling life on land to occur. And it's also, like I said, the locus of a lot of interesting geochemistry, which we'll discuss later in this class. So that's all I have for you. Next, we're going to launch into a discussion of what solutes we find in water around the world and what drives the production of those solutes. So thanks for listening. Bye.